Hey everyone, welcome to another video. To start off, I can ask you to please like and subscribe. It'll help us out a lot and help us to keep making these videos to teach you guys how to code and hopefully ace your next technical interview. I'm here again with our mechanical engineer.
Hey there.
There he is. So last time we covered a really simple sort of code screen for a lot of internships called FizzBuzz, where you basically are just looping through to a number n and printing fizz or buzz depending on if the number is divisible by things. So now we're going to start covering a little bit more towards the algorithms side of computer science and software engineering in general. So we're going to start off with binary search. Do you know what that is?
Yeah, I think so. So, but like as far as I know, binary search is when you're searching through, a list or something along the lines of a list, and then you go to the midpoint and then you see if, that first chunk is where you are looking for your number, whether that number is there or if it's, in the second half chunk there, and you keep splitting, your list in half until you get down to your actual number that you're looking for.
Right. So the general idea is that you're, dividing by 2 or splitting it in half to basically improve the runtime of your searching, if that makes sense. So just as a warm up, I'm just going to ask you to define a list. You can make it like sequential, like you can just do 1, 2, 3, 4 up to 10. We'll make it sorted. So just define some list here. Right. And then if I just said to write a one-liner in Python to find or return true or print true if the number 6 is in our basic list, what would you do?
6 in basic list.
Yeah.
Return true, right?
Yeah, and then you'd print true, right? Yeah. So return true if it's a function, print true if it's not. Yeah, exactly. So the problem with that, though, is what's actually happening when you use that in operator is we're going to be looping through the list as if we did like for I in list, checking every single iteration. So technically, if our number wasn't in it, or if the number was 9, for example, we would have to loop through our entire list. So one of the benefits of binary search is that, like you said, we're cutting it in half every time. So this is under the assumption that we have a sorted list in order to do the math behind it. So what we can do instead is, in terms of like time complexity, I think we've mentioned it in the past, but the runtime of doing if 6 in basic list is going to be O of n, meaning we have to go through n times. But with binary search, we can get to log n runtime, assuming we have a sorted list, which is basically log base 2, if you're familiar with how that math works out. And basically that just means, if you had an input of, say, 32, then we'd only have to run it 5 times because 2 to the 5 is 32. So it's kind of just the inverse of the exponent. You're familiar with that. So remember, it's log base 2. That's really important.
Okay.
So anyway, why don't we just write a function called binary search?
Okay. All right.
Sure. And this will take in a target and a list. You can call it whatever you want.
The list, or do you want a different list?
Sure. Whatever you want. Anything other than that, just because I don't want you to get confused about the list at the top there. So let's just call it like S list or something. Other list, sure. Okay. So you mentioned binary search. So to start off with this, we basically are reassigning a window at every iteration, right? So in order to do that, we need to have sort of 2 pointers, 2 bounds, which you can call left and right. And then we're gonna have what do you think left would be in the first time we get in there?
The list 0, right?
So that'll be the actual element, but let's think of these as our indexes rather than the actual element themselves. So to do that, you would just
0, yeah.
0. Okay, yeah, because we're gonna move these indexes around and then check the element at that index, right? And then that's gonna be
len, which is but that's going to be inclusive, right?
Yeah, so the length of the one at the top there is 9, but remember it's 0 index, so you gotta subtract 1 to get rid of that off by 1 error. All right, cool. So now we have our window defined for our first pass through. And what we're doing throughout this loop is we're going to reassign left and right. So our 2 pointers, we're going to reassign them to shrink our window in half, depending on the midpoint of that window, if it's larger or less than the target element. Does that make sense?
Yeah, yeah.
All right. So to do this, we're going to use a while loop. And then what do you think our condition would be, considering that we're taking, because there's a chance that our target is not in there. So at what point do we know, using binary search, that our target is not found in our list?
If we get through the whole thing and we don't find it, then we know it's not in there, right? I guess that didn't really explain it.
So what defines when we get through the whole thing with the variables we just assigned there? What is the condition that those two variables will have?
If left and right are equal to each other, that means we got through the whole thing, right?
Right, but that's right. But instead, you could just do while left is less than or equal to right, because that's always going to basically keep it on our left, the left on the left and the right on the right. If they cross, then we're dead, right? All right. So then what you can do now, and to get in the habit of doing this, is we just talked out loud about what our condition is if it's not found. So for our error condition for this function, you can return -1 if this condition is no longer true. So all of our logic is going to be in this while loop here. So outside of the while loop, you can just say return -1, which means that we did not find it. And as the programmer, we'll know that if we call this function and we get -1, that it's not found, right?
Okay.
So now, what is, if you remember our base case from recursion, right? Something very similar here. When the first thing we want to do is see, well, first of all, actually, before we get into that, we have to define our midpoint, right? So now it'd be really easy to say that our midpoint is just, the length of the list divided by 2. That would give us the midpoint. But the only thing is, if you remember, we're going to be reassigning left and right.
Yeah.
So it's a little bit mathy, but what do you think, how would we define the midpoint regardless of what left and right is, under the assumption that left will always be less than right?
Well, since we're redefining left and right multiple times, I assume, in this while loop, then wouldn't it just be left plus right divided by 2, like the average of them?
Yeah, exactly. And then just to be sure, I would use floor division, which is just two slashes. So I would just enforce that we always take the floor. All right, cool. So now we have that part done. Sort of basically our midpoint is our reference point throughout this whole algorithm, right? So remember that what left, right, and mid are, they are indexes, right? So the first thing you're probably going to want to do is see if that middle, if in our list at that middle index, if that is our number. And if so, then we can just return the index, which in this case is middle. Yep. So now remember, what is middle here?
Middle is our midpoint.
And now, but what you're saying there on line 14 is if middle equals target.
We want other list parentheses middle, right?
Brackets, yeah.
Brackets, yeah.
We're indexing a string on this variable.
Yep.
Sorry, excuse me. And then don't forget double equal for comparison. I think I'm going to do a lesson where I just make you type comparison.
Double equal, yeah.
So that basically says if at our midpoint that we just computed, if, so in the top, in the list on line 1 that you have, it's probably 5, I think, or 4. So if we get there, then we're good. So now, if we get to this next point, then that basically means that we didn't get our target, right? So we have to split the list in half. So how do you think we're going to do that? And then what are the two cases that we have based on our midpoint? What are the 2 options we have?
If the midpoint is less than the target, that means that the target is kind of higher up in our other underscore list. So that means you have to shrink that again. That means we can probably add to our midpoint, and we can make that the new left, and then the right can stay, and then we'll shrink it again eventually.
Yeah.
And
So
then
why don't you type up that conditional?
Yeah. So, if middle, no, I want this.
Yep.
Is less than target.
Right. So what do you want to do if our midpoint element is less than the target?
So we need to assign left again.
Right.
Left equals this, correct?
Now, is it going to be that? Because remember, what are left and right?
It needs to be just middle.
Yep. We're messing around with our indexes here. We're not going to mess around with limits, right?
Mm-hmm.
Okay.
Mm-hmm.
So now, do we want to set it to middle, or because what do we know about what's at middle?
Needs to be elif. Sorry, what was the question?
So what do we know about middle, though? We just checked if middle is in the target. So do we even really want to look at middle ever again, or can we just do left equals
plus one? Yeah. Mm-hmm.
All right, and then there's one other case, which is kind of the inverse of that last one you wrote there.
Yeah, and I think that needs to be an else, because I think we want to go through these sequentially, right?
Yeah, we want to do one thing per pass, exactly. So the return will catch you for the top one, but this is a good way to do it, yeah.
Okay, so, or, yeah, I guess else. Or
you could do another elif, but I would do an else here because, no, I would do another else, or I'm sorry, excuse me, an else because, you know, in terms of how numbers work, there's really only three options. It's either equal, less than, or greater than. So we know because of how just, numbers work that this case is when the element at middle is greater than target. And then, the -1, that'll cover that. So, and then, let's bring, he ran away from you there, but, all right. Okay. All right, cool. So let's see the whole function. Just, very cool. So now this looks pretty good. I think this is right. So why don't we just call this and let's make sure that we got everything good to go. And I think you can call with the list that I think sorted list was what you called it. So you can actually just use that. And then target, you can put, 4 or something. Right. And then just print this and hopefully this prints the index of 4 in that list, which should be 3, I believe. Okay. That's very much. Oh, that's going to be, scroll up on line 5.
No.
Yeah, just get rid of it. There you go. Okay. So now, just to talk about the complexity here, so I mentioned that looking through something, a list of size n all the way through is going to be big O of n, right? So n times through the list. Binary search here is going to be log of n, which is significantly faster because you have, 10 elements here? And, 2 to the 3 is 8. So we really shouldn't have to loop. That while loop won't execute any more than, 3 or 4 times versus 9 times to get the exact same output. So some of the sort of takeaways is this is the idea of kind of having these windows that we reassign pointers is really important in technical interviews and just software engineering in general. So, messing around with indexes with some input to kind of get what we want, that's really important to have that, be able to multitask in your brain, right? And say like, this is an index versus the element itself and reassigning stuff, right? So the idea of having these pointers move around is really important. And then also just note that if this list isn't sorted, this doesn't work.
Gotcha.
But yeah, good job. You got to that pretty quickly.
Cool. Thank you.